All right, 3.4, we're going to continue to talk about limits, more specifically one-sided limits, which we've kind of talked about a little bit. So we're going to talk about limits coming from the positive direction and the negative direction, and also continuity. So we talked about continuity of a polynomial, so just whether a polynomial is continuous or not. We're going to talk about continuity of a limit on an open interval. So open interval is going to have parentheses. We'll also get to continuity on a closed interval at the end of this section, but right now we're just focusing on the open interval. So you can say that a function f is continuous at x equals c. It means that there are no interruptions in the graph of f at c. That is, the graph is unbroken, there are no holes, no jumps or gaps. So on the next page we have 3 examples of graphs that are not continuous. So these would be discontinuous is the word that they use here. But these are not continuous. So if you were a little ant and you were crawling from A to B, your 2 values on your x-axis from A to B on that interval, if you can't make it all the way across from A to B, then it's not continuous. So a hole means that it's not continuous. If you have a gap here, not continuous. Even if you have a point that's on your graph, so if f of c exists, but it's not the same as the limit of f of x, not continuous. So these are the 3 examples that you'll see not continuous. Also, if you had something, which kind of goes for the gap, but if you had a graph that looks like this would be not continuous. Can't walk across your graph from one interval to the other. So these are not continuous. So the definition of continuity at a point, a function is continuous at c if the following 3 conditions are met. If f of c is defined, so if f of a value exists, if the limit as x approaches c of f of x exists, so you need the limit to exist, and the third thing is that the limit as x approaches c of f of x has to equal f of c. So these 2 things have to be the same. A function is continuous on an open interval a to b if it's continuous at each point on the interval, and a function that is continuous on the entire real line from negative infinity to positive infinity is continuous everywhere. We're also going to talk about discontinuity. It's going to be removable or non-removable. So if something's not continuous, if it's discontinuous, we could have discontinuous that's removable or something that's non-removable. Removable discontinuity is if there's a hole and you can fill that hole with exactly 1 point. So if you're able to fill the hole, that would be removable. You could just pick up a point and replace it. That is removable discontinuity. If it's a gap where your graph can't just be filled by 1 little point, then it would be non-removable. So in A here on the left, this would be removable discontinuity because we can just fill that gap. So this is removable. For B, this would be non-removable. You can't make it continuous with just 1 little point. So that would make it non-removable. And then C would also be removable because we could make it continuous with that 1 little point there. We could fill the hole. So we want to discuss the continuity of each function. So when we're talking about whether it's continuous or not, it helps to know what the graph looks like. So f of x equals 1 over x. This is one of those graphs that I told you, it helps to just have memorized what it looks like. You could always just plug in values and see, but our graph of 1 over x is going to look like this. Would this graph be continuous? No. It would be discontinuous. And is it removable or non-removable? Non-removable. We just can't make it continuous with one little point, so this is non-removable. And it's discontinuous. At what value makes it discontinuous? 0. X equals 0. So it'd be discontinuous at x equals 0. If it asks for a specific interval, let's say if it asks us specifically on the interval, let's say from 1 to 10, would it be continuous on the interval from 1 to 10? Yeah. So it could specify on a specific interval, is it continuous or not? This one's discontinuous at x equals 0. It'd be discontinuous from negative infinity to positive infinity. But if we specified, we could say that it's continuous from 1 to 10. It'd be continuous everywhere except at 0. Let's look at B. So let's graph B first. What a graph. Let's simplify. How can I factor the numerator? X plus 1, x minus 1 over x minus 1. Does anything cancel? X minus 1s. So we have a whole where? At x equals what? 1. So we've got a whole at x equals 1 because it canceled out. So I'm just graphing x plus 1 with a whole at x equals 1. So if I were to graph this, my y-intercept would be 1, so I'd put a point there, and my slope would be 1 over 1, so I'd go up 1 over 1. But I've got a whole at 1. So up 1 over 1. So our graph would look like this, with a hole there. Is this continuous? No. It would be discontinuous at what point? At x equals 1. We're talking about the x value. So at x equals 1, it is discontinuous. Would it be removable or non-removable here? Removable. We could fill that hole with just 1 point, so it would be removable. Let's do C. So same thing, we're going to graph, but we have a piecewise function here, so we're going to graph both pieces. So if I plugged in 0 to my first one, I'd get 1. And that would be a closed circle there. Now it's a line, so I'd go up 1 over 1, but we're just going in the negative direction, so down 1 over 1. So our line would look like this for the first part. What's the shape of the second piece of my graph here? How do I know what the shape of this is going to be? A parabola, awesome, because it's x squared. So we're going to start at 0, but we've got a hole at 0. So if I plugged in 0, I'd get 1. We've got a hole there. Let me pick a different color there. And then if I plugged in 1, I would get 2. If I plugged in 2, I would get 5. So our graph would look like this. Is this continuous? What do we think? If I was a little ant and I was walking along my graph, at any point would I fall? No. This is continuous because our first piece of the piecewise function stops at the same part that it starts again. They overlap there. This is continuous. So we would say continuous. It'd be continuous from negative infinity to positive infinity. So on our whole graph. Any questions there? Let's do D. What's the shape of an x squared graph? We just did it in the last one. A parabola. So we're going to have a parabola here, and our vertex is going to be at 0, 0. Would this be continuous? Yes. Continuous from negative infinity to positive infinity. Next page has the graphs of each of them, which is what we did. We graphed it to help us see if it was continuous or not. Let's look at, we'll call this example 2 because it's a different example. So we're doing the same thing here. We're discussing the continuity of the function. So let's graph it. We're going to graph both pieces of our piecewise function. So for my first piece, what's the shape of this going to be? A line. It's in the form of y equals mx plus b, so it'll be a line. So if I plugged in -1, I would get 1, so I can put that point. Go to the left 1, up 1. Is it going to be an open or closed circle at that point? Closed circle. If I plugged in -2, we'd get 0. Then our slope just goes up 1 over 1. So if you wanted to keep putting points, you could, but our first part is going to look like that. For our second piece, what's the shape of our second piece going to be? A parabola, because it's x squared. So if I plugged in -1, I would get 0. So is it a open or closed circle there? Open. What if I plugged in 0, what would we get? -1, so I've got a point there. If I plugged in 1, I would get 0. If I plugged in 2, you get 3. So our parabola looks like this. Is this continuous? Nope, not continuous. So we'd say discontinuous. Is it removable? Nope, it would be non-removable. We just can't fill a hole and make it continuous. So this is non-removable. At what value is it discontinuous? At x equals what? At x equals -1. Perfect. And then just for extra practice here, what if this asks for f of -1? What is f of -1? One. Awesome. It'd be this point here because this was the closed circle. So f of -1 would be 1. What about the limit as x approaches -1 of f of x? What would this be? What would our limit be? Does not exist. Awesome. Go ahead. Because we approach two different values coming from the left and coming from the right, the limit as x approaches -1 does not exist. Next, we're going to talk about one-sided limits. So we can break our limit apart, which we did kind of in the first section where we introduce limits. We can talk about a limit coming from the negative direction. So this would be a left-sided limit, because negative numbers are on the left. Or we could talk about a limit coming from the right direction or the positive direction, which would be a right-sided limit. We know that if they approach the same number, so if the limit as x approaches c from the negative direction and from the positive direction were the same value, then that would be what our limit of that number would be. Or if the limit exists, then the left-sided limit and the right-sided limit are going to be the same thing. We're also going to talk again about the greatest integer function. So that's kind of like the absolute value with the 2 bars in it. This is the greatest integer such that n is less than or equal to x. So less than. So if I had the greatest integer of 1.3, what would this be? 1. Awesome. What about -1.2? What would this be? -2. What about the greatest integer of -10? negative 10. Perfect. All right, so let's look at example 2. So here we're finding our one-sided limit. So the limit as x approaches 0 from the negative direction. So 0 would be here, but what would our limit be as we approach from the negative direction? Negative 1, awesome. That would be coming from this way, so that would be negative 1. What about the limit as x approaches 0 from the positive direction? It doesn't matter. It doesn't matter. Yeah. Well, like, it depends, because it doesn't matter when you're taking the limit, because we're talking about where our graph approaches. But if we asked for, like, f of 0, then you would want the closed circle. What about, what's our limit as x approaches 0 from the positive direction? 0. What is our limit as x approaches negative 1 from the positive direction? So our negative 1 is here. From the positive directions coming from the right. So what would that be? Negative 1. And then the limit as x approaches negative 1 from the negative direction, what would that be? Negative 2. If it asks for the limit as x approaches any integer, so we'll say the limit as x approaches a for our step function here, where a is an integer. What's an integer? A whole number. If we were asked to find not a one-sided limit, but just a limit of the limit as x approaches 0, any integer, any whole number, it would not exist. So that's why for our greatest integer function or any step function, we would use one-sided limits. Because if I were asking for the limit as x approaches 1, at 1, coming from the left and coming from the right, we approach two different values, so this would not exist, does not exist. So when the limit from the left is not equal to the limit from the right, the limit does not exist. And then here we have a theorem, the existence of a limit. So the limit of f of x exists if and only if the limit coming from the left is equal to the same number as the limit coming from the right. Let's say I had the limit as x approaches, we'll just call it 1, of f of x equals 5. What would the limit as x approaches 1 from the positive direction of f of x be? What about the negative direction? So if our limit equals 5, it would be 5. So if our limit exists, that means the limit coming from the positive direction and the negative direction are going to be the same thing. All right, next we're going to talk about one-sided limits on a closed interval. So really all that means is that f of a has to exist and f of b has to exist. So these have to be closed circles if you're talking about a closed interval. So here it says the limit as x approaches a from the positive direction, so coming from the right, of f of x has to be equal to f of a. So f of a has to exist. Same thing as the limit as x approaches b, so our right-handed limit here, the right side of our interval, but from the negative direction has to be the same as f of b. So they have to be closed circles. It's really all this is saying. If we're talking about a closed interval, then those values have to exist. Similar definitions can be made to cover continuity on the intervals of the form of A to B. So if you have an open and closed interval, and a closed or open. So these are neither open nor closed when you have one of each, but we do it the same way. So here, if I were asked to find the limit as x approaches 2, of 2 minus x, what would this equal? What would the limit as x approaches 2 be? We're talking about the negative direction. If I plugged in 2, what would I get? 0. And then if I were to ask what g of 0 is, or g of 2, sorry, g of 2, if I were to plug in 2 into here, g of 2, what would g of 2 be? Also 0. So because these are the same values, we can close the bracket there. I mean, it's kind of the same idea as domain. Like if we were to be asked what the domain of this would be, it's the same. You're doing it the same way. I don't really think that there's any questions like this on the web assignment. I don't think that this comes up because it's really just asking if it's continuous or not. So you'd find the domain and where it exists. And then if it's closed circles at the end, it would be brackets. So you guys kind of already know how to do that. Because whatever's under our square root has to be greater than or equal to 0. So that's kind of why we get the bracket. So it's the same idea as domain. So in example 3, we want to discuss the continuity of f of x. So f of x equals the square root of 1 minus x squared. So first let's talk about our domain of this function. So for our domain, we know that whatever's under our square root has to be greater than or equal to 0. So we get 1 minus x squared is greater than or equal to 0. Two different ways that we can solve it from here. What could we do? Any suggestions? We could do that, but instead of subtracting 1, it may be easier to add x squared. That way we don't have to divide by negative. Because if we divide by negative, remember you have to flip your inequality. So we can add x squared. We get 1 is greater than or equal to x squared. What would we do next? Square root both sides. So here's where we kind of get into a little pickle. We have two values, right? Because what's the square root of 1? Plus or minus 1. So I'm going to say x equals plus or minus 1. But since we have two values, we got to put it on a number line. So I have -1 and 1. Would they be open or closed circles on my number line? Closed, because it's less than or greater than or equal to. That equal to makes them closed. We can test a value. I would say let's plug in 0. It's right in between -1 and 1. If I plug in 0, does it work? We have 1 minus 0. Can I take the square root of 1? Yes. So in between works. So we're talking about the interval from -1 to 1. With brackets, because we know that it was a closed circle. Our graph of our function here would go from -1 to 1. We know that they're closed circles because we could plug in -1 and 1 and it would exist. But what the book kind of wants you to think about is the limit as x approaches -1 from the positive direction. So if we are coming from the right side here, as we approach -1 from the positive direction, does that exist? Or can we put a bracket? So the limit as x approaches -1 from the positive direction of our function 1 minus x squared, what would that be? If I plugged in -1, what would we get? Or if you look at the graph, what's our y value as we approach -1? 0. Is this the same as f of -1? If I plugged in -1 into my function here, do we get the same thing? Yeah. And then let's check the right side. So the limit as x approaches +1, but coming from the negative direction, since we're coming from the left now, of our function 1 minus x squared, what do we get? What do we get? 0. Is this the same as f of 1? Yeah. So because they're the same, we can say that our function here is continuous on the closed interval from -1 to 1. All right, so you have homework to work on. There's a couple questions from the homework that I will say that make you think a little bit. If the question asks, find the values where f is discontinuous, you're looking for where it's undefined or where you have a hole. So if it gives you a function and it asks to find the values where f is discontinuous, you're looking to see where your function's undefined or where your function has a hole, which is the same idea. There's also a couple questions, like piecewise function questions. Let's say we had the piecewise x plus 1, and I'm making these numbers up, so they're not going to make sense. But let's say actually we'll call it bx plus 3. It's going to ask you as x is greater than, we'll start with as x is less than 1 and x is greater than or equal to 1. It'll ask you find the value of b that makes this continuous. So if our piecewise function is continuous, they're going to leave off and pick up in the same spot. So our first graph would be, if I plugged in 1, I would get 2. So our first piece would look like that. The second piece, you want to find what value, when you plug in 1, would give you the same number. So when you plug that in, it overlaps. So you're looking for what value of b would make it continuous. I don't want to do it for you. I want you guys to try. Maybe start with these questions since we didn't really practice any of them. See if you can figure it out. You guys have 25 minutes still in here, so work on the homework. Ask questions. I want you guys to think about it a little bit.